Geometry lesson 6-3. Continuing our discussion with parallelograms, we talked last time about the different things we learned that we know we will have as a fact from parallelograms. That opposite sides will be the same. They'll always be congruent opposite sides. We also know that opposite angles are going to be congruent to each other. We also talked about the fact that diagonals will be bisected. So whatever diagonals are inside your parallelogram, each diagonal will bisect each other. All right? And we also learned that there's some supplementary characteristics between consecutive angles. Now we want to look at this concept that if you have one pair of opposite sides of a quadrilateral that are congruent and also parallel, then that has to make it a parallelogram. So if you can prove, if you're being asked to prove, you can look at the concepts we had from last time, which would be if you could prove all the angles in such a way that the opposites were always the same as each other, they were congruent, then you'd know you have a parallelogram. If you could prove that these two sides were the same and these two sides were the same, then you know you have a parallelogram. But you also can use this concept that if you can prove that these two sides are the same and parallel, then you know you have a parallelogram. You don't have to worry about the other two because that's how they would get locked in. So looking at this right here, this is the concept of them being the same measurement, and this is our symbol for parallelity, so they would be parallel to each other. I'm not worried about these two. The only way that this wouldn't work, imagine if this line were longer, therefore it wouldn't be congruent, and the only way it connects would be like this, and those clearly aren't parallel to each other. The only way it would happen is if that line were extended. But that's not the case we're given. We're given the fact that these two are the same, which means it's going to lock that into a specific spot, and it's going to lock these angles in, which are all the relationships we talked about for parallelograms to begin with. So say we had a given situation where we had some coordinates, and we want to show that these coordinates produce a parallelogram. One method is to look at the slopes, because all parallel lines have exactly the same slope. So if you look at this graph here, one of the easiest slopes is the A to B. Because it has no rise, but it does have run, this slope is going to be 0. So A to B, slope is 0. As well as D to C, the slope is 0. So the fact that we have parallel lines here is a good start. Okay? We also know that we can find the parallel, or we can find the slope for these lines. Rise over run. 1, 2, 3, 4, 1, 2. 1, 2, 3, 4, 1, 2. Looks to me like the slope from A to D is 4 over 2, which is 2. And on here, 1, 2, 3, 4, 1, 2. 1, 2, 3, 4, 1, 2. It has the same slope, 4 over 2, which is 2. And now I know that this side is parallel to this side, which fits our description of all parallelograms. We'll have opposite sides that are parallel to each other. So we've now proven with one method that you can in fact say that is a parallelogram. Another method would be to look at the sides. So the lengths of the sides. Now that's a little bit more difficult. On A and B it's not too hard, you can just count. 1, 2, 3, 4, 5, 6, 7, 8. It's 8 units across. So from A to B, the length equals 8 units. And D to C is pretty easy to count. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that's a good start. We know we have 8. But A and D are a little harder. And one thing you can do to find the lengths of A and D is think about the fact that this is producing a right triangle. And when we have a right triangle, we can use the Pythagorean theorem. Now, it goes up 1, 2, 3, 4, 5, 6, 7, 8. And it goes over 1, 2, 3, 4. So we just need to find the hypotenuse. And remember, the hypotenuse is going to be equal to each leg squared. So we could say for A to D that it's going to be 8 squared plus 4 squared is equal to C squared. Well, that's 64, and that's 16. So we know we're dealing with, when we add these two together, a total of 80. 80 is equal to C squared. Which means, if you put the square root on there, those cancel out. C equals the square root of 80. Now I could simplify this down, and I could find perfect squares that go into it and break this radical down into a simplest form, but I don't really need it. As long as I can compare BC and get the same thing, I'll be okay. And what you'll notice is, on B to C, it produces another right triangle that's 8 and 4. And I'm pretty sure that if that triangle is 8 by 4, and this triangle is 8 and 4 and produced a square root of 80, then we're going to get another square root of 80. And there we have it. You have two sides that are parallel, or are the same length. So this is the same length as here, and this is the same length as up there. And so because the two opposite sides are the same length, you know that you have a parallelogram. And lastly, you could combine those. You could have one pair of opposite sides that's parallel and congruent. I think the easiest ones to count are the horizontal lines, where we said AB and DC were equal to 8 units. And we had AB was parallel to DC because the slope equaled 0 on both of them. So the fact that I'm looking at this right here, we have parallel and congruent means you must be dealing with a parallelogram. So you don't have to do all three methods. I just wanted to show that you could use a culmination of different methods. If this one's best for you, great. If that's the kind of information that makes it easy, use that method. If you find it's easiest to use this method right here, do that one. If you want to find the lengths of all the sides and compare the opposites, that would work too. But any of them would work. It's whatever you're dealt with and you want to use that makes it easiest for you.